Welcome to Chemistry for 10+2. Dear students, today we are going to deal with chemical properties of alcohols. But before starting with that, subscribe my channel, like it and share it with your friends. So let's get started. Today we are going to see chemical properties of alcohols. The reactions or the chemical properties which we are going to deal with are as follows. Reactions involving breaking of CO bond in alcohols. In this, we are going to see reaction with hydrogen halide, reaction with phosphorus halides, dehydration, wherein we are going to see formation of alkenes and oxidation of alcohols. Dear students, let's begin with the reaction. Reactions due to breaking of CO bond in alcohols. We are going to see here reaction with hydrogen halide. Alcohols react with hydrogen halides to form alkyl halides. ROH. This is the general formula of alcohols. When it is treated with HX, that is hydrogen halide, X can be any halide group. As we can see here, Rx is removed, that is alkyl halide is formed and water molecule is removed. The order of reactivity of hydrogen halide is Hi is highly reactive, then HBr, and HBr is reactive than HCl. HCl is less reactive than HBr, hence Lucas reagent, that is concentrated HCl plus anhydrous ZnCl2, that is zinc chloride, is used. Alcohols are soluble in Lucas reagent, while alkyl chlorides are not and produce turbidity in the solution. Tertiary alcohols react rapidly with hydrogen halides. Secondary alcohols react somewhat slower, and primary alcohols even more slowly. This is known as Grove's process. Let's talk about the reaction with hydrogen bromide. Alcohols, when heated with HBr, it forms alkyl bromides. As we can see here, this is ethanol, CH3, CH2, OH plus HBr gives, as we can see here, the highlighted part consists of water and this bromine gets bonded to CH2. Thus, formation of bromoethane takes place, which is an alkyl bromide, plus HBr, H and OH forms bond to give water. HBr is prepared in situ by adding sodium bromide to hydrochloric acid or sulfuric acid. Ethanol on heating with hydrogen bromide gives bromoethane. HBr is stronger than HCl, so no need of ZnCl2 catalyst. In case of HI, also there is no need of catalyst. Let's see the reaction with hydrogen bromide. Secondary alcohols react with hydrogen bromide to form alkyl bromides. Here it is secondary alcohol, that is propan-2-ol. When it is treated with HBr, it gives 2-bromopropane plus water molecule is removed. Propan-2-ol, that is secondary alcohol, reacts with hydrogen bromide to give 2-bromopropane. Let's see the reaction with tertiary alcohols. Tertiary alcohols react with hydrogen bromide to give alkyl bromides. 2-methyl propan-2-ol is a tertiary alcohol. When it is treated with HBr, it gives tertiary alkyl halide, that is 2-bromo-2-methyl propane plus water molecule is removed. The tertiary alcohol 2-methyl propan-2-ol reacts with hydrogen bromide to give 2-bromo-2-methyl propane. Let's see the reaction with hydrogen iodide. Alcohols react with hydrogen iodide to form alkyl iodides. Here, this is propane-2-ol. CH3CH3 bonded to centrally placed carbon atom is OH group plus HI. It forms 2-iodopropane and water is removed. Most of the alcohols do not give acceptable yield of alkyl iodides. Propan-2-ol, that is secondary alcohols, react with hydrogen iodide to give 2-iodopropane. No zinc chloride catalyst is required as HI is very strong acid. Let's see the next reaction, that is reaction with phosphorus halides. First we are going to see reaction with phosphorus trichloride. Ethyl alcohol reacts with phosphorus trichloride to give ethyl chloride plus H3PO3. Isopropyl alcohol, when treated with phosphorus trichloride, gives isopropyl chloride and H3PO3. Tertiary butyl alcohol reacts with PCl3 to give tertiary butyl chloride and H3PO3, that is phosphorus acid. Let's see the reaction of alcohols with phosphorus halides. Here we are going to see reaction with phosphorus tribromide. PBr3 is less stable and hence prepared from red phosphorus and bromine in situ. Ethyl alcohol, when treated with PBr3 in the presence of red phosphorus plus Br2, this on reaction gives PBr3, which reacts with alcohol to give ethyl bromide and H3PO3 as the byproduct. Here we require 3 molecules of ethyl alcohol. Let's see the reaction with secondary alcohol. This is isopropyl alcohol. When it is treated with PBr3, it gives isopropyl bromide, and phosphorus acid is also there. Tertiary butyl alcohol reacts with phosphorus tribromide. It gives tertiary butyl bromide. And phosphorus acid is seen. Let's talk about the reaction with phosphorus halide, that is Pi3 here. Phosphorus triiodide. Pi3 being less stable is prepared from red phosphorus and iodine in situ. Ethyl alcohol. 3 molecules of ethyl alcohol when treated with Pi3, that is phosphorus triiodide, reacts to give ethyl iodide. Similarly, isopropyl alcohol reacts with Pi3. Reaction condition is to be given red phosphorus plus I2. On reaction, it gives Pi3, which reacts with alcohol to give isopropyl iodide. Tertiary alcohols react with Pi3. It gives tertiary butyl iodide, and phosphorus acid is removed. Now we are going to see the reaction with phosphorus halides, PCl5. Ethyl alcohol, when treated with PCl5, it gives ethyl chloride plus HCl plus POCl3. POCl3 is phosphorus oxychloride. Similarly, isopropyl alcohol reacts with phosphorus pentachloride to give isopropyl chloride, and tertiary butyl alcohol reacts with phosphorus pentachloride to give tertiary butyl chloride. Let's see dehydration, formation of alkenes. Alcohols undergo dehydration to form alkenes on treating with an acid like concentrated sulfuric acid or H3PO4 or aluminum. This is an alcohol. On treating with acid, it is found that H and OH of adjacent carbon atoms are removed and formation of double bond in between the two carbon atoms is seen, giving rise to the formation of an alkene, and water molecule is removed. Removal of water molecule is known as dehydration. Ethanol, that is primary alcohols, undergo dehydration by heating it with concentrated H2SO4 at 443 Kelvin. How the reaction is taking place? Let's see. This is ethanol. In the presence of 95% concentrated H2SO4 at 443 Kelvin, removal of water molecule takes place and formation of alkene is seen. Let's see the dehydration reaction in case of secondary alcohols. Secondary alcohols undergo dehydration by heating with 60% H2SO4 at 373 Kelvin. Propanol, that is propan-2-ol, undergoes dehydration in the presence of 60% concentrated H2SO4 at 373 Kelvin. Water molecule is removed and formation of propene is taking place. Similarly, when we talk about the dehydration of butan-2-ol, 60% H2SO4 in the presence of temperature that is 373 Kelvin, we find water molecule is removed. Here, the two adjacent carbon atoms from which H and OH are removed, possibilities of two different products is seen. It depends upon the alpha and beta carbon atom from which H and OH is removed. In the first case, we find formation of but2-ene is seen. That is CH3, CH, double bond CH, CH3. Whereas in second case, you find the carbon atom from which hydrogen is removed is this one. So H of this carbon atom and OH of this alpha carbon atom gives rise to the formation of the product that is but1-ene. Here but2-ene is the major product. This is Sercev's rule. What does this Sercev's rule tell us? Let's understand. In dehydrogenation or dehydration, the alkene formed by elimination has greater number of alkyl groups attached to the doubly bonded carbon atom. As we can see here, to this doubly bonded carbon atoms, we find this is the first alkyl group and this is the second alkyl group. In but2-ene, there are two alkyl groups, whereas in but1-ene, only one alkyl group is attached to doubly bonded carbon atom. So, the major product obtained here is but2-ene, which is following Sercev's rule. Let's see dehydration in tertiary alcohols. Tertiary alcohols require only 20% H2SO4 to undergo dehydration at 363 Kelvin. Tertiary alcohol taken here is 2-methyl-propan-2-ol. 2-methyl-propan-2-ol undergoes dehydration in the presence of 20% H2SO4 at 363 Kelvin. Water molecule is removed and formation of alkene, that is 2-methylpropene, is taking place. 2-methyl-propan-2-ol when treated with 20% H2SO4 at 363 Kelvin gives 2-methylpropene. The relative ease of dehydration of alcohols follows the following order. Tertiary alcohol is greater than secondary alcohol, which is greater than primary alcohol. Let's study the mechanism of intermolecular dehydration of alcohols. Tertiary carbocations are more stable, therefore easier to form. Let's study the mechanism of dehydration of alcohols to form alkenes. Intramolecular dehydration of alcohols involves following steps. Alcohol is protonated by the acid. This process is fast. Thus, protonated alcohol is obtained. In the first step, alcohol gets protonated to form protonated alcohol. In second step, protonated alcohol forms carbocation. Let's see how. Formation of carbocation. This is protonated alcohol. This step, that is formation of carbocation, is a slow step. Second step is slowest and it is rate determining step of the reaction. Here, this oxygen and this carbon bond gets broken down and the electron moves to the oxygen atom to form carbocation and water molecule is removed. In step 3, formation of alkene is taking place. The carbocation obtained, that is CH3, CH2, where carbon atom is positively charged, can be written in this way also. This carbon-hydrogen bond gets broken down and the electron moves in between the two carbon atoms to form the double bond, resulting into the formation of alkene. H positive is removed. In the third step, elimination of proton gives rise to formation of ethene. Acid used in the first step is released in the third step. Dear students, now we are going to see oxidation of alcohols. Oxidation of alcohols involves the formation of carbon-oxygen double bond with cleavage of OH and CH bonds. Let's see how the cleavage of OH and CH bond leads to the formation of carbon-oxygen double bond. Here, this is an alcohol. Breaking of CH and OH bond leads to the formation of carbon-oxygen double bond. As we can see here, this hydrogen atom is hydrogen from alpha carbon atom, and this hydrogen is hydrogen from OH group. Which leads to the formation of C double bond O. This is known as dehydrogenation reaction, which involves loss of dihydrogen from an alcohol molecule. Depending on the oxidizing agent used, a primary alcohol is oxidized to an aldehyde, which in turn is oxidized to a carboxylic acid. Let's study oxidation of primary alcohols. A primary alcohol on oxidation using acidified potassium dichromate first gives an aldehyde which on further oxidation gives a carboxylic acid. Here K2Cr2O7 is potassium dichromate. When treated with H2SO4, that is an acid, forms K2SO4 plus Cr2SO4 thrice plus H2O and oxygen. Here K2Cr2O7 is orange color. After reacting it with acid, formation of Cr2SO4 thrice takes place, which is of green color, and formation of oxygen is taking place, which is responsible for the oxidation of alcohols. So here ethanol undergoes oxidation in the presence of acidified potassium dichromate, gives an aldehyde CH3CHO, and the highlighted part carrying water molecule is removed. Giving rise to the formation of ethanol, that is acetaldehyde. Ethanol further undergoes oxidation to give ethanoic acid. Both aldehyde and acid formed contains same number of carbon atoms in alcohol. Aldehydes are more readily oxidized than primary alcohol. Aldehydes can be separated by distillation due to large difference in their boiling point, avoiding further oxidation, which works only in lower members. It may not work in higher alcohols or aldehydes due to small difference in their boiling point. Let's see oxidation of alcohols. A best reagent for obtaining an aldehyde from primary alcohol is pyridium chlorochromate, PCC. CH3CH2CH2OH, that is N-propyl alcohol, when undergoes oxidation in the presence of pyridium chlorochromate, it gives CH3CH2CHO. Propanol is obtained. PCC, that is pyridium chlorochromate, is a complex prepared by mixing chromium trioxide with pyridine and HCl in dichloromethane. PCC is a mild oxidizing agent which oxidizes primary alcohols to aldehyde. C5H5NH positive CrO3Cl is PCC, that is pyridium chlorochromate, oxidizes primary alcohols to aldehydes. Further, formation of acid does not take place. Let's see here secondary alcohol. Secondary alcohol on oxidation using acidified potassium dichromate first gives a ketone which resists further oxidation. This is propan-2-ol, the secondary alcohol. When it undergoes oxidation using acidified potassium dichromate, as it can be seen here, water is removed and formation of acetone, that is propanone, is taking place. Ketone formed contains the same number of carbon atoms as in alcohol. Ketone resists further oxidation as it involves breaking of C-C bond. Secondary alcohols can be oxidized by ketone. Secondary alcohols can be oxidized to ketone by PCC, that is pyridium chlorochromate. Let's see oxidation of tertiary alcohols. Tertiary alcohols can be oxidized by using strong oxidizing agents like acidic potassium permanganate or CrO3, which dehydrate alcohols to alkenes and then oxidize. Here is the reaction. 2-methyl-propan-2-ol, which is a tertiary alcohol, undergoes oxidation in the presence of CrO3 to form alkene, that is 2-methylpropene. Tertiary alcohols resist oxidation as there is no alpha hydrogen atom. Further, 2-methylpropene forms propanone and CO2 is released. Aldehydes are more readily oxidized than primary alcohols. Let's talk about dehydrogenation of alcohols. Under the topic, reaction due to breaking of CO bond in alcohols. When vapors of primary or secondary alcohols are passed over heated copper at 573 Kelvin, dehydrogenation takes place. Here, ethanol is a primary alcohol. When it is passed over heated copper at 573 Kelvin, it forms an aldehyde, that is ethanol, and water molecule and hydrogen is removed. Dehydrogenation is taking place. When secondary alcohol is passed over heated copper at 573 Kelvin, formation of ketone, that is propanone, is taking place and removal of hydrogen is taking place. Now we are going to see dehydration of alcohols, that is tertiary alcohols. Tertiary alcohols undergo dehydration to give alkenes. 2-methyl-propan-2-ol is a tertiary alcohol. When it is passed over heated copper at 573 Kelvin, water is removed and formation of alkene is taking place, that is 2-methylpropene. Dear students, if you like the way of presenting, please subscribe my channel, like and share it with your friends. Thank you.